IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond to you individually. Today, we welcome Richard Speer, Product and Technical Services Manager at Cable Components Group, Connecticut, USA, who will be presenting his paper on the future of material selection criteria for power over local area networks. Richard Speer is the Product and Technical Services Manager at Cable Components Group, LLC, specializing in the development and application of high-temperature, chemically foamable materials. Previously, Richard was the TE Connectivity, AMP, NetConnect, and worked as a Senior Development Engineer and Product Development Engineering Manager for premise cable and connectivity. He holds a BS in Business Economics from High Point University, as well as a degree in Mechanical Engineering. Richard has been in the wire and cable and connector industry for over 35 years and holds 5 international patents. He was an active member of TIA 42.7 for 13 years, a member of NFPA, and is currently a UL Standards Technical Panel member for UL 13. Richard, we welcome you to present at today's IWCS webinar series event.
Yeah, thank you, Ed. I appreciate the introduction, and I appreciate everyone that's called in for this webinar. So today our webinar is the future of material selection criteria for power over local area networks. Certainly I'm doing the presentation today, but a lot of people put a lot of work into this presentation. So I'd like to give credit to these guys. Stephen Lee is a doctoral student at Rensselaer Polytech. Rami Asisnik, I call Dr. Rami. He is a polymer scientist and a professor at Rensselaer Polytech. And Charles Glew, who is the president of Cable Components Group, and certainly over many years has done many white papers and contributions to our industry. The 2017 National Electric Code adds a limited power designation, which allows higher currents in data cables to power various devices in the premise environment. Power over Ethernet is certainly not something that's new to our industry. And I think it was 2002, Power over Ethernet first was ratified, and TIA worked on it. And so Power over Ethernet has been around for a good long while. The difference between what we're talking about now and what we were talking about then was the addition of higher currents. And with these currents, you do produce more heat in data cabling. So as a former cable designer, I tend to think of things as a cable designer and from that viewpoint. So in this presentation, what I'm going to do is talk to you primarily as a cable designer and as I think about things that I would think about in designing a cable. In the past, a cable designer for premise, you really thought about transmission characteristics and about flame testing. Those were the only two things that you really had to give much consideration to. Certainly, cables that you design have to pass the UL criteria or testing, NFPA 262 or 1666. And you had to do your transmission characteristics to meet the TIA ISO standards. This new standard within the NEC gives you another thing that you have to consider. I think of it as a stool with three legs. So one leg is transmission, one leg is safety, and now one leg is power. So when you look at the NEC and what's happening is, again, they're allowing more power into these applications. And cable components, it did a significant amount of research in this area, and that research is the foundation of this paper. So let's take a look at the 1987 NEC cable hierarchy. At that time, when we looked at this cable hierarchy, certainly it was a disruptive technology. For the first time, it put cables in a hierarchy. So you had the plenum cable on the top, then followed by riser, general purpose, and limited use cables. So within this, I think we all know that you can work down, but you can never work up. So a plenum cable could be used in a riser application, a riser cable in a general purpose cable application, but you could not use a general purpose cable into a riser application, nor a riser cable into a plenum application. So let's take a look at the National Electric Code. Specifically, we're looking at Article 725, which is your Class 1, 2, and 3 power-limited circuits. It affects Article 770, 800, 820, and 830. And the key changes to these articles are there is now a limited power designation, and you can have anywhere from 0.5 to 1 amp within these cables if they meet the limited power criteria. Now, what's driving these? What is driving this technology? When you look at it, you can see that this red line represents lighting. At this point in time, in 2016, you can see that about 10% of the lights are LED. But as you move up to 2022, you can see over 50% of the lighting is going to be LED lighting. You can look at wireless access points. Again, you're at about 45%. In 2022, you're going to be about 82%. PoE to the desk, 80% now, but you'll see it up over 92 to 93% by 2022. These are just some of the drivers for this technology. In my work history and currently I have an opportunity to work with some really, really smart young engineers. And I like to think about this from their viewpoint. These engineers have lived with the internet and the web their entire life. They've had it from early childhood until now. They really understand the technology. They understand apps and app-based technology. And this technology is really as large as these young engineers' brain. So when you think of it in that terms, and you think of young engineers that truly understand what can be done and see applications, it's a pretty big application for us in our industry. The work we did was at Underwriters Laboratory, and I'd like to just briefly go through the test that we did in Underwriters Laboratory. We did the LP testing per the requirements that Underwriters Laboratory has set forth for this particular power over LAN cables. What you'll see as we go through this, you have one center cable, which is shown on this slide. And then you'll see various bundles around this center cable. When you look at the construction, what you'll actually see is 3 bundles of 64 cables. So at the end, you end up with 192 cables. That's within a bundle. The bundle is kept very tight. There's no loose cables in there. Everything is, all the cables are sitting beside itself. This picture shows the center cable, And you can see you have a thermocouple here that actually goes inside the jacket into where the pairs are located. I've had the question is, are those pairs stripped? Have you taken the insulation off of the wires within this cable for this thermocouple? And the answer to that is no. This thermocouple is put inside the cable. It's sitting on the insulated pairs as close to the middle of those pairs as we can get. You also have a thermocouple on the outside of the jacket, as you can see here. So during the test, the center cable in all of our testing showed that the center cable was the hottest cable, or got the hottest from the current. So you're looking at, in this case, temperature within the cable, temperature on the jacket of the cable. And we'll talk more about that in just a moment. This is a picture of the engineering technician at UL putting the center thermocouple inside the jacket. There's a slit made in the jacket, and the thermocouple is inserted into that jacket. This is a picture, and I think this is a good picture to take a look at the actual setup for the test. This is the fixture at UL as we were doing one of our tests. And as you can see, this is the 192 cable bundle here. It's all wired in series. So all the cables are connected. You've got all four pairs connected together as we go through this. Interesting enough, this is, again, 3 bundles of 64 that produce 192 cables. It's sitting inside the conduit, and in this picture you can see that. One of the interesting things about this picture is it does show that the cable does not, in this case, fill up the entire conduit. In fact, in this area there was 1 to 1.5 inches of airspace around this cable. Once you put the conduit surrounding it, you can see that the conduit was added on top, and in this area there is fire stop in both this area and this area. So within this space there's no air movement. It's completely sealed off. I'd also like to say that all these thermocouples are located in the center of this conduit. If you drew a plane across this part of the test itself, you put a plane through there, all these thermocouples are in that plane. So you don't have one thermocouple in the middle, one thermocouple in the next layer 2 feet away, and the next thermocouple 3 feet away on the other side. All these thermocouples are within the center plane. When you look at the LP testing, let's talk about this just a second. You can see that the bottom of this test is a half amp, going up to 1 amp. The voltage is pretty constant at 200 volts, which equals these watts, anywhere from 100 to 200 watts. Now, I'd like to say the important part of this and understanding this is that the four pairs are connected in series. So what you end up with is a fourth of this on each pair. For instance, at 1 amp, you can get 200 watts, but that's 50 watts per pair or 100 watts per circuit. I'd like to talk about where the thermocouples are located. At CCG in our testing, we actually added more thermocouples than UL normally has within their test. We talked about the center cable. You can see the center cable here in a 6-around 1 construction. So we had thermocouples on the inside of the cable and outside of the jacket in this center. The 6-around 1 configuration, we had a thermocouple on the outside of that. Then you went to 19 cables, 37 cables. Again, we had a thermocouple on each of these layers. At the 128 and the 192. So we wanted to look at the thermal gradients as you move radially from the center out to the outside of the cable. There's one thermocouple that's not shown in this diagram, and this is the thermocouple that's sitting out here. There was actually a thermocouple on the inside of the conduit. So we looked at the differences in temperatures from the center cable all the way out to the inside of the conduit. The results of that testing, I think this is a very interesting slide, especially from a cable design point of view. It shows you exactly probably what you anticipated, in that your 24 gauge, which is represented by the blue line, definitely gets hotter at the same current and voltage than the other 23 or 22 gauge. 22 gauge, as we would all think, got less hot because, as we all know, the resistance of the 22 gauge is much less than a 24 gauge piece of copper. So from a cable designer's point of view, when I look at this chart, at 24 gauge, you're at 100 degrees C. Now, these temperatures have been adjusted for 45 degree ambient. The actual testing is done at 20 degrees C ambient. And to get to the 45, you subtract the 20 to get to 0, add 45, and that adjusts the ambient temperature to 45 degrees C. So when you look at that within this test, the 24 gauge cable was right at 100 degrees C. So to pass this test with a 24 gauge cable, you would need 105 degrees minimum rating on this jacket, on the cable itself. So 24 gauge, even at a half amp, is, from a cable design point of view, maybe not the best alternative to choose from. When you look here, you have a 22 gauge. Certainly as far as heat production is concerned, you produce much less heat with a 22 gauge. One of the issues with 22 gauge, as we all know, number one is cost, in that the cost of the copper is significantly more than a 24 gauge, as well as terminating a 22 gauge into an RJ45 connector, whether it be a plug or a jack. The RJ45 connectors are made that 22 gauge can be terminated into them, but it's not easy. I've terminated many of these cables into connectors and used 22 gauge wire. And while it can be done, it's just not easy to do. So that leaves the 23 gauge, at least from a cable design point of view, is probably the best alternative to look at as far as conductor size. So when you look at this chart, you can see that at a half amp, at a 23 gauge wire, you're approximately 75 degrees C. This is a chart that looks at the same information in a little different way. Again, we talked about in 2002 time frame that power over Ethernet first surfaced. You were talking about a current of 0.175 amps, wattage of 35, voltage of around 50 volts. At that point in time, we didn't really worry about heating, because at those levels in here, there really was any temperature. You could see that there was a 5 degrees temperature change. As you move up in current, as can be seen in this column, you see 0.3. There were certainly iterations of power over Ethernet since 2002. There was a PoE plus. I also think Cisco had a PoE application that was higher than the 0.175 amps. And you can see as you move into this territory, you do start to see some overheating. As you go into 0.5, you can see that you're at a 44 degrees temperature change. As you move up into 0.7, you can see that this cable is starting to overheat. At 0.9, you're seeing extreme overheating with your temperatures. And when you get to 1 amp, you're seeing the very extreme overheating in these premise data cables. So when we think about these temperatures and we talk about materials, what we've done here is we've put temperature ratings, typical temperature ratings for premise cables into a table, and you can see it along the bottom the materials that actually fit within this temperature zone. So at 75 degrees C, you can see LDPE, polypropylenes, high-density polyethylenes. They live within this temperature zone. As you move up to the 105 degrees C, you can see that semi-rigid PVCs live within this temperature zone. As you move up to the 150 degrees C, which is less than 0.8 amps, you're looking at PVDF. And moving forward, you can see that all the materials moving forward from here are all fluoropolymers. And as you move up the 200 degrees C, FEP, as you get into 250 degrees C, MFA, PFA. And again, as our hierarchy within the NEC for flammability, you can see the same thing within this chart for materials. As you move up, if you look at the highest rating of 250C, you can see PFAs, MFAs. You can always move down. You can use MFA in 105 degree C cable, but you could not use 105 degree rated PVC in a 250 degree C cable. So it follows this hierarchy as far as NFP 262 and plumb testing. So we looked at various cables within this. We went and purchased cables on the open market and tested these cables. And once we found out that 23 gauge was the best alternative from a cable design point of view, we focused on 23 gauge wire. So everything that you see from this point further into the presentation is all with 23 gauge wire. And let me say that all these cables, the 23 gauge wire was measured and was 0.224. So all the conductors were the same in all cables. We looked at a shielded construction, and as you can see, as you look here at 0.6 amps, if you look at the highest temperature, now these temperatures, let me change one thing, is we looked at these temperatures and these charts are in Fahrenheit. We switched from Celsius to Fahrenheit for these charts. So when you look at these cables in the shielded construction, you can see at 0.6 amps, you are around 225 degrees C. This is the center conductor in this area for a shielded cable. And you can see for foamed FEP construction that you're slightly less. You're in at about, let's say, 235 degrees C. As you move outside from the inside of this bundle toward the outside, you can see in this case that these temperatures seem to get wider, the difference between those. The all foam construction we built at Cable Components Group, it was a foam FEP insulation. The insulation was 30% foam. There was a foam crossweb. The crossweb was 38% foam, and a foam jacket. The jacket was 20% foam. All these materials, FEP, all of them foamed. So when you look at this, you can see, again, even at a half amp in the center, you can see that the shielded cable had released more heat than the foam cable. Now let's look at solid versus foam materials. At 1 amp, which would be your highest temperatures, at 1 amp, a solid fluoropolymer insulation produced about 340 degrees. Again, this is on the Fahrenheit scale. And these numbers are adjusted to 45 degrees C. 1 amp of a foamed fluoropolymer was around 295. So you can see there's a difference in the heat released into this test between a solid product and a foam product. When you look at the half amp on the other end of this spectrum, you can see that the solid was in at about 205 degrees F. The foam construction in at about 170 degrees F. So what this is telling us from looking at this chart, as well as the previous chart with the shielded products, is that foam constructions tend to insulate the heat better than other constructions. This is a pyramid that we assembled looking at materials. And again, if you look at this side, you can see temperatures. These temperatures are typical temperatures that cables, premise cables are made, and typical ratings for materials. So when you look in the 75 degrees C, you can see for halogenated materials, again, you're talking about polyethylenes, polypropylenes. We also added this non-halogenated materials, as these engineered resins are becoming more and more popular in our marketplace. So you can see you have low smoke, halogen-free polypropylene, as well as polyethylene. When you move up to 90 degrees C, you're talking about low smoke PVCs. 105, you're at PVC. As you move above 125, you're looking at PVDFs and PVDF copolymers within this temperature range. 150 to 200 degrees C, you're looking at ECTFE, ETFE, as well as engineered resins of PSU, PES, PPSU. From 200 degrees to 250 degrees, you're looking at FEP, MFAs, and PPSs for non-halogenated materials. The 250 degree level and above, you're looking at PFAs, and on the non-halogenated materials, PEC and PEEP. So in our conclusions, let me go through these just briefly with you. In the test, the materials must match the temperature rise in a power over LAN cable test. In the real world, these cables will be put in cable trays or bundles within cable trays, and will have a heterogeneous makeup of materials within the 60 degrees C and 75 degrees C rated materials. They will be dominating most of the cable within these trays. So one of the things we need to be cognizant of is that thermal stability and low heat transfer to these adjacent 4-pair cables is an important characteristic. So we want to take and emit as little heat as possible into the cables within this tray. Through our research, we found that foam materials have a benefit of low heat transfer, and they're very thermally stable, so that the heat transfer will be minimized to the adjacent cables within this cable trays. Foamed FEP and MFA demonstrate the character resistance at higher temperatures to minimize heat transfer while being very thermally stable. They were shown to be able to carry more current, and at this current, emit less heat to this test. In this test, the cable as a whole must withstand elevated temperatures. A standard 4-pair 24-gauge power over LAN, subjected to even a moderate level of amperage, in this case 0.7 amps, must withstand 153 degrees C, and that's with a 45 degrees C ambient. Accordingly, PVCs and polyolefins cannot be used as this material within these maximum temperature ratings of 105 degrees C. Therefore, at 0.7 amps, the heat rise without ambient is 108 degrees C. So the temperature rise at 0.7 amps without adjusting for the 45 degree C ambient already exceeds the 105 degrees C. This adaptation of the limited power standard in the 2017 NEC is a transfer, can't say that word this morning, certainly disruptive technologies, requiring installations, crosswebs, tapes, and jackets to be extruded with a broader range of materials in both solid and foam. And again, when you think about cable design and you think about a stool, you deal with transmission properties, you deal with safety issues and burn testing. Now you're adding power, another leg onto this stool. So as a designer thinks about what he has to work with in designing these cables, material selection and the thermal stability of this material selection must be considered. Thank you.
And thank you, Richard. At this time, we will ask as many questions from the attendees as time permits. And I would start with this first question. How do you reconcile these temperatures with the traditional 40 degrees C and 60 degrees C performance tests of the UL 444?
With the 60 degrees C, let's talk about the 60 degrees C. When you look at that, with a 24 gauge wire, it's just not a material that you could use in this test. It is a material you can use within cable construction, but you wouldn't be able to get a half amp with a 24 gauge wire. But as you move down in gauges, as you can see, as the copper gets bigger, less heat. So to use these type of materials in that range, you would have to use a larger copper to pass this test.
Okay, and I would just like to follow, the same submitter followed on with this. Typically, the cable is supposed to transmit power over Ethernet and data simultaneously, but the UL 444 test is only up to 60 degrees C. How is the cable material supposed to behave, or how does UL look to this high temperatures of PoE?
I'm thinking about this. Yeah, I'm considering this question. Excuse me, I'm sorry. It's early in the morning, and yeah, you know, Southerners, they are a little slow anyway. So the typical cable in this 444 is 60 degrees C. Is the cable that's been used in the past. However, as we move up in current for these applications, you can use the same conductors probably, but the jacket is going to have to be a higher temperature rated material. As far as how UL looks at this temperature rating in the form of PoE, that's probably a better question to ask those guys.
Okay, thank you. Next question. Are you aware of any halogen-free materials that are used in communications data cables that will be able to withstand the temperature rise from powering at 100 watts or greater, and also meet the tray, riser, and or plenum cable fire safety requirements?
Yes, let me move back to a slide. Move back again. When you look at this pyramid you can see has two sides. You have the halogenated materials and the non-halogenated materials. So there are non-halogenated materials that can withstand these temperatures of the new limited power tests. Next question.
Okay. Yes, next. Does the heat or energy radiate outwards from the conductor? And if so, can this potentially impact adjacent cables in a bundle, even if they aren't powered directly?
Yes, the heat does radiate from the cable outward, and it can certainly affect cables within a cable tray, other cables in a cable tray, in a couple of ways. One is we know that the cables in existing cable trays are typically 60 degrees C jackets, in this case with FEP insulation, so your cable has a 75 degrees rating. So as you put these higher current cables in that tray with these cables, you can certainly see that more heat is going to be radiated to these cables. The other thing we need to consider is that a lot of these cables have been in these trays for quite a long time. Materials, as we know, do change over time under heat, and many of these materials, especially the non-fluoropolymer materials, tend to get somewhat brittle. It's not necessarily a problem in existing structures because these materials are not been around, they're not moved. But when you put the higher temperature cables in the tray with these cables, there certainly could be a concern that there could be heat issues within these buildings.
Okay. I have one more question for now. Just remind, I'll ask this last question. If anybody has one more to ask, please do so now. Since the cable needs to meet the appropriate temperature rating to account for the temperature rise when powering the cable, do all the cable components and materials such as the insulation, separators, and jackets also need to meet this temperature rating?
In the LP test itself, it is based on the temperature rating of the jacket. So if the jacket is rated, in this case, let's just say 75 degrees C, as you move up in current, you can't exceed this 75 degrees C rating. So with the 24 gauge wire, with your standard constructions, as long as the cable doesn't get over 75 degrees C, you will get that rating. In this case, let's say it's a half amp. If you went to 0.6 of an amp, that temperature is going to go above the 75 degrees C rating. So at that case, it would not qualify for 0.6 of an amp. In this presentation, we focused only on plenum cables. So the materials used to pass a plenum NFPA 262 test would require that the components within the cable, which would be the conductors as well as a filler or anything else in there, to pass the NFPA 262 test. As most of us know or certainly have tested themselves, to my knowledge, there is not a non-fluoropolymer solution to a plenum test. So the components within that cable certainly have to be able to withstand those temperatures, as well as the jacket.
Okay, great. At this time, I have no further questions, so I would like to thank the people who submitted questions, and also thank you, Richard, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Richard after today's event. Each of these IWCS seminar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 Eastern USA time. Our next scheduled webinar event will be on Friday, November 18th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 60 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 8th through Wednesday, October 11th, 2017 at the Gaylord Palms in Orlando, Florida, USA. In addition, the inaugural regional UL and IWCS China 2017 Cable and Connectivity Symposium will take place on Tuesday, April 25th through Thursday, April 27th, 2017 at the Marriott City Center in Shanghai, China. Please visit our website at IWCS.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank Thank you for participating, and this concludes today's event.